Hello. So, it's been a while. Today we're going to look at a theorem you may or may not know, a formula called the shoelace formula, and we're going to relate that to Green's theorem. So, it's a really cool formula. I actually don't remember how to prove it the elementary, the regular way, but know how to do the overkill method we're going to look at today. So, first of all, what's the shoelace theorem? So here's the idea. In the xy plane, imagine you have this polygon and you have the coordinates of all the vertices of that polygon. It turns out there's a really nice formula, an unexpected formula that allows you to find the area of this polygon. This area of the polygon. And it goes something like this. So it allows you to find the area of the polygon in terms of the vertices. So the area is equal to, okay, I've written stuff out like this. You'll see why in a second. So here's the idea. You're going to multiply like this, all the down and to the right diagonals, and add those up. And at the same time, you're going to subtract the backward diagonals. And maybe now you see why it's called the shoelace theorem. It looks like shoelace when you put it like that. So in the end, you're going to have x1, y2, and then you're going to subtract the reverse one, y1, x2, and you're going to do the same thing with the next bit. So x2, y3, and then the reverse one, you're going to subtract that product, and you get minus y2, x3, and you keep going on like that again and again until the very end. You're going to have it wraps back around. You have xn y1, however many vertices you had in your polygon, minus the backward diagonal, yn x1. So that's a really neat formula. So you can try it for yourself. I don't know, plot a triangle, use the formula, and it turns out you get exactly the area using this, a bit of an enigma. I have some comments on this actually. One comment is, what if you just looked at 2 points? Obviously it's nonsensical, but the process reminds you a lot of taking the determinant in 2 dimensions, doesn't it? Because, you have this diagonal, you have the backward diagonal here, right? You multiply that, you subtract the product of the other ones. It turns out there is a relationship with that, if you think about it. But I'll leave that for you to discover yourself, or you can find some reading somewhere. I probably read that on Wikipedia somewhere, but just reminded me of it now. Okay, so now we're going to talk about Green's theorem, just as a review, or maybe you've never seen it before. So here's the idea. That's the statement of Green's theorem. It's that the integral, so it will help if I draw a picture here. Imagine you have some region in R2. It says that the line integral taken counterclockwise along the boundary of this arbitrary region of p dx plus q dy is actually equal to the area integral. I don't know if that's what you call it, region integral perhaps, on the inside of the boundary. So suppose the region is called D, we'll denote the boundary by C. Well, C taken counterclockwise and whatnot. This is very cool, but maybe you need a little more inspiration for it. So you might have seen this before, but I'll do it anyway. Now, anyone who's done some line integrals is familiar with the technique in Green's theorem where you split it up into a bunch of little regions so that the partial line integrals are going to cancel out. So something like this. Gosh, I should put down this book. It's really weighing me down. Okay. Something like this. This is my region. Something like that. Very scary because, it's not nice and smooth. I have a circle, another circle inside. How the heck do I take the line integral of this? So here's the technique. You split it up into some nice ones that have a clear inside and an outside, and a nice clear boundary, a nice inside region. And then you'd be allowed to apply Green's theorem, because now you have a region on the inside, right? So if you split it up like this, you can imagine you have one that goes like this. Okay, I'll need to draw a little more here. One region like that, that's like the left part of this donut. And then you have another region here, the right part of the donut, that's also counterclockwise. Sorry, I'm struggling with my directions a little bit here. So that's the idea. And when you take the line integral around here, you add it with the line integral around here. Is that the original line integral we were interested in? As in this circle and then that circle? The answer is yes, because these line integrals, well, they follow the same path, but they go in opposite directions. If they go in opposite directions, you actually get the negative, right? Like, think back to fundamental theorem of calculus in one dimension. You have integral a to b of f of x dx. Well, you know that's going to be based on the endpoints and whatnot, and that's going to be the negative of the integral taken in reverse. And you don't need the fundamental theorem of calculus to show this. It actually just holds true for Riemann integrals and whatnot. But that's one way to think about it. So going along this contour, this line, and then going in the opposite direction, you add up those line integrals, because this big line integral is just the sum of these two smaller ones and all their components, and they cancel out. And in the end, it means you can break it up like that, do those two integrals separately, and it's the original two circles that you wanted to deal with in the first place. Okay, maybe I went a little long there. Oh no. Okay. It's okay, guys. Okay, now here's the idea. What if I have a region like this, and I want to break it up into smaller regions, because the big one is just too much to deal with. So I don't know, something like that. And I will say this is still going to be taken counterclockwise, because that's just the convention. Okay, something like that, and we're taking it counterclockwise. Like that. Well, we can break it up as much as we want. So this is a nice simple region, it doesn't have an inside part that we're subtracting like before, but it is still a bit of a challenge because there are just so many parts. But anyway, the idea is you can split all these up like that and like this and so on. And you notice each one of these little regions, there's also a nice line integral around it, and you can keep breaking it up into smaller and smaller pieces. So let's see if I can reproduce. Okay, that's okay. Doesn't look quite the same, but anyway, imagine you break it up into very little pieces, very, very fine pieces, and each little piece looks a little something like this, or you can approximate it and say that they're little circles if you want. But if you think about it, a little circle, what does that remind you of? It reminds you of the 2D curl, right? It's how much it spins counterclockwise. And 2D curl is given by this thing right here. Oops, this should be a q with respect to x. The partial of q with respect to x minus the partial p with respect to y. So the actual idea behind Green's theorem, and this applies to the generalized Stokes theorem in higher dimensions too, is that summing up all of these little line integrals, when they get small enough, it's like summing up a bunch of little curls. So it explains why the line integral, the overall curl, if you want to think about it that way, is the sum of all the little curls on the inside of the region. So I hope that gives you a little intuition for why Green's theorem is really, really cool. Okay, so that's enough of that. Enough of a tangent. Let's move on. So that's the shoelace theorem, that's Green's theorem. Let's put them together. Put them together how? Well, over here there was some idea of going along the boundary, sort of. I mean, we only looked at the vertices. It sort of feels like we're tracing out the boundary. And at the same time, well, we want to find the area. And as you may or may not remember, the area of some region is nothing more than the double integral over that region of 1 dx dy. And that makes sense because, well, a similar thing will hold in one dimension, right? If you had a function, or if you did not have a function, you wanted to find the length. So instead of area in one dimension, you want to find the length. That's nothing more than the integral over some interval. And instead of having some function, you have 1 on the inside. Okay, maybe that's not clear, but the length of an interval AB is nothing more than the integral over AB of 1, which is b minus a. Same thing applies here. So that's established. You might need to think about that a little longer. I'm not sure if I explained it the best way. But using this idea, we can apply Green's theorem to sort of hopefully change this area problem we have into a contour problem, into a line integral problem. And you might think, what are you doing? Why are we going to line integrals? This is just basic geometry. Well, yes, but it's also really cool to use Green's theorem, and you'll see. So the idea is we want to get the area by having the integral of 1 dx dy. If we look at Green's theorem, we just want to make the integrand here equal to 1 somehow. In other words, we want to choose very strategically a p and a q such that the integrand is 1. And here's the p and q we're going to choose. You have infinitely many options. Here's what we're going to do. So I'm just going to copy down what we had back there. Now, what if q is equal to 1/2 x and then p is equal to minus 1/2 y? Well, then the partial of q with respect to x, I'll write it as qx, is going to be 1/2, and then the partial of p with respect to y is going to be minus 1/2, but 1/2 minus negative 1/2 is going to be 1. So that's our choice of q and p, and it's very clever. So we're going to use that so we can take advantage of Green's theorem. In other words, we can find the area by just doing some line integrals now. So this is going to be the line integral around the entire boundary of whatever region we're doing. We haven't gone specifically to the shoelace theorem yet. In fact, the formula I'm about to show you will hold in general. Okay, so p dx is going to be minus 1/2 y dx, and then q dy is going to be 1/2 x dy. So the line integral around any region of minus 1/2 y dx plus 1/2 x dy surprisingly is going to give you the area of the region on the inside. So it doesn't matter what region you have in R2. Maybe, is that the only blob I can draw? You have something like this. I want to find the area on the inside. It looks like such a scary shape, right? But luckily I can parametrize it, and using that parametrization I can parametrize the boundary, and using that parametrization I just do the contour integral here, and very nicely I get the area without needing to deal with trying to find I can break this up like that, I can define that by a function. It's just very messy. So that's cool. That's the relationship we have right now. How does this relate to the shoelace theorem? Well, I just showed you that thing there applies to any region in R2. So why not apply to this specific region in R2? Namely, the one that has the boundary formed by a bunch of line segments, which is a polygon. So, what am I going to do? I'll continue writing. Let's not erase the board just yet. We want to find the area, and we just said that the area, or we just showed that the area is equal to this line integral using Green's theorem. Very nice. So here's what we're going to do. When it comes to a polygon like this, we're going to split it up into a bunch of sub line integrals. So, you know, maybe we'll call this first bit from x1, y1 to x2, y2, c1. So this part is c1, and that part from x2, y2 to x3, y3 is going to be c2, and so on. The last one is going to be cn, and that takes us from xn, yn back to the starting point, x1, y1. So here's the idea. This is going to be nothing more than not a circle, it's not going to be a closed line integral anymore, but line integral c1 of this junk, and then same thing for the next one, because the line integral of the entire path, the entire contour, is nothing more than the line integral of parts of the contour along the way. So we carry on all the way up to, I'll make this clearly an ellipsis, up to cn of that same junk, and then we're done. So all that's left is we need to parametrize each of these lines and then evaluate the integrals, add them up, and hopefully that gives us a nice expression. So here we go. I'll clean up the board and we'll be right back. Okay, we're back. So what do we have to do now? We need to parametrize each of these line segments, and nicely, parametrizations of line segments is pretty easy. So we want to find this first one, c1, which goes from the point x1, y1 to x2, y2, the first point to the second point. How do I parametrize this? Well, here's how I always think about it. I think of it in terms of vectors. So how do I get from this vector x1, y1 to the other vector x2, y2? Well, the vector that connects them is going to have components x2 minus x1, y2 minus y1. So if I just scale this with values from 0 to 1, you can imagine if t equals 0, then I'm at the starting point, x1, y1. If t is like 1/2, I'm half the way there to x2, y2. And if t is equal to 1, I've made it all the way. So if I let t take on all the values from 0 to 1, then I'm going to include the values along the line segment just as we wanted. So that's the idea. To actually do it, let's write it out in full form. X is going to be the starting point plus this vector that connects the first point to the second point, x2 minus x1. And same thing for the y coordinate here. y1 plus t, y2 minus y1. Okay, great. I'll erase that for a little bit of space. That's our parametrization. And remember, when we're doing integrals with the parametrizations, we actually need to find a way to replace these differentials, dx and dy. Because in its current form, what are we supposed to do with that, right? So we'll find the differential here. Dx is equal to, so taking the derivative of both sides with respect to t, this x1, it's a constant, so it vanishes. In the end, we get x2 minus x1 dt, because the t becomes a dt. Same thing here, you're going to get dy is equal to y2 minus y1 dt. Okay, great. So with all that set, we're ready to substitute back into this first line integral that we wanted to evaluate. So we're going to have the bounds, t going from 0 to 1, because we just said that's what gives us the line segment. And then we just make the substitution for every other part. Okay, I made a mistake earlier. So that's probably been cut out in post-production and whatnot. So we have this thing, that's our that's our y substituted, so minus 1/2 y, and then dx is right here. Dx is x2 minus x1 dt, and then the next part is 1/2 x dy. So 1/2 plus 1/2 x by our parametrization is x1 plus the vector that connects the 2 points, and then dy, which is y2 minus y1 dt, and you know, you can factor out the dt, not really what happens, but you can merge these two integrals together, so we don't have to deal with, you know, both parts separately. And it turns out that's nice because these expressions are very similar. Hopefully there are some nice cancellations. So from here it's a little messy, a bunch of algebra, so let's work on it together. We'll go through it together. Let's first factor out this 1/2 to make things a little easier for ourselves, and then let's distribute some things here. So I see this x2 minus x1. Let's distribute to both parts here, and similarly with the y2 minus y1. And let's see what that gets us. I'll do the positive part here first because I really don't want to deal with the negative sign right now. So we have x1, y2 minus y1, and then we have plus t x2 minus x1, y2 minus y1. Okay, so far so good. Let's deal with the first part here, the negative part. It becomes minus y1 x2 minus x1. And here's something really nice already. We multiply those together, it's a minus, it's the minus here, minus t y2 minus y1 x2 minus x1, like that. But wait a second, this looks familiar. They're exactly the same. And this one has a negative sign, so they end up making 0. So that's pretty good. We only need to work with this part of the expression now, over on the left. So in the next step, the next line, I'm going to expand it some more. And what do I have? This is going to be x1 y2 minus x1 y1. Then I have minus y1 x2 plus, I'll write it as x1. Yes, I'll write it as x1 y1. Let's take a look at this, and then, oops, dt. Let's take a look at this, and look, another cancellation right there. Amazing. So you might be thinking, how do we get all these nice cancellations? What in the world? So I've tried this before, this application of Green's theorem to find areas, and it really matters what you choose for P and Q. Again, there were an infinite number of choices. Why did I pick minus 1/2 y and 1/2 x? Because, you know, they look very similar, so hopefully somewhere in the algebra, I'm like hopeful, because they both have the factor 1/2, they're both to the first power linear, so hopefully as we do some parametrization, enough symmetries are there that it cancels out, and in fact it does cancel out really nicely. So, you know, if you want, give it a shot with a different choice of P and Q and let me know how it goes. Right. So we have the minus x1 y1, the plus x1 y1. Those are gone now. And in the end, we have that the integral over this first line of our entire line integral is nothing more than 1/2 integral 0 to 1 of x1 y2 minus y1 x2. Is your mind a little blown yet? Because look at this. That's exactly what came up in our expression up here. So you probably see where this is going. And integral 0 to 1 of this, not bad at all, because this entire thing, it's a constant. So integral 0 to 1 of a constant is just that constant. x1 y2 minus y1 x2. Okay, I'll clean up the board and we'll get back to work. Alright, this is where we left off on the last board. We found that the line integral along the first line segment connecting points 1 and point 2 is going to be 1/2 this strange little, these strange terms here, this expression that we saw pop up earlier. And now you see where this is going. So we're not done. You know, you might think, that's not the whole thing. You're right, it's not. We only did the first part of the line integral. We need to do each other line segment along the way. So, in fact, I don't need to show you the work again because, well, it's just renaming of these constants. So, when we went from point x1, y1 to x2, y2, this is the expression we got. Now if we go from the point x2, y2 to x3, y3, it's going to look like this. So, you know, I hope you appreciate that reasoning. I'm really not going to go do the work again. It was quite a lot of algebra. And then you do that for all of them. The final one, of course, is going to be the little different one because it wraps around. It's going to be 1/2. Instead of going from x1, y1 to x2, y2, we're going to go from xn, yn to x1, y1, like that. So, just by symmetry, you don't need to work all of these out again. And remember, we want to find the area, which is the integral around the whole thing, which is the sum of the integral along each line segment. So in other words, we add up all these integrals like that, and we get, you know, the closed integral along C, which is the entire boundary of our polygon, and that's going to be of minus 1/2 y dx plus 1/2 x dy. That's going to be equal to, and you'll notice the 1/2 factor. Let's factor that out right before. It's going to be x1, y2 minus y1, x2. And then add up this for the second line segment, plus x2, y3 minus y2, x3. And then you keep going for all the ones in the middle, no matter how many sides your polygon has. And you have the last one here, xn, y1 minus y1 minus yn, x1. Sorry. That's exactly the shoelace formula. Look at that. We derived and we actually proved the shoelace formula using Green's theorem. So, huge overcomplication. I hope you appreciated this look at Green's theorem intuitively, how it's the sum of these little curls, how we derive this nice formula here, this expression that allows us to find the line integral of any closed region we can parameterize, and then, well, using that to find the formula for the shoelace theorem. So, there you have it. Thank you for watching.